Welcome everybody to day 3 of this online workshop on advances in many-body theories from first principle methods to quantum computing and machine learning. And I'd like to welcome the first speaker of today's session, which is Giuseppe Caleo. He will be talking about variational methods in the era of machine learning, classical and quantum computing applications. So if you can share, that looks good.
Okay.
I will just hand it over to you.
Right? Okay. All good. So thanks for the introduction, and thank you to all the organizers for having me here today. It's really a pleasure to be, even though only virtually, at ECT Star. It's a great place, and I really like. I always enjoyed the conferences I've been attending there. So today I'm going to tell you about some advances in the use of machine learning techniques and also the development of new machine learning techniques to study many-body quantum problems. Specifically, I will discuss some applications mostly in the context of quantum condensed matter and a bit of chemistry. But I mean, in the next talk from Alessandro, you will learn more about this idea. In general, I'm going to show you today is rather general. It can be applied photo of some rather fundamental methodology that can be applied to a lot of different subfields where the many-body problem is a key problem, right? So, and this brings me actually to the first concept that I wanted to introduce, which is this concept of corners of the Hilbert space. So what do I mean by that? Well, essentially, and I mean, as I was mentioning, one key problem that arises in several subfields, so including nuclear theory, condensed matter, chemistry, and quantum, even quantum computing, is essentially related to the fact that if you have a many-body wave function, then this object is a rather complex object to handle theoretically and also, I mean, in some cases experimentally. But I mean, from a theoretical standpoint, the issue is that, for example, if you have a wave function of qubits or, I mean, of spins, 1/2 in this case, then you know that the number of coefficients that in principle you need to store to just represent this wave function is exponential. So if you represent this as a superposition of all the to the n possible states, in this case of qubits, then you know that you have 2 to the n coefficients, and because of this complexity, because of this exponential complexity, solving things like the Schrödinger equation, the time-independent one or the time-dependent one, or even the Lindblad equation, which is an equation for open quantum systems, if rho is your density matrix. All of these problems are intrinsically exponential because of this underlying complexity of the wave function in different subfields. However, I mean, if you look at this, and essentially just the space that you would need on a classical computer to store the wave function of, let's say, 54 qubits, you would immediately, if you do the math, you will realize that you will need the entire summit, the best supercomputer or so, at least until last year, to store just the wave function coefficients. And in the past 5,000 years, our ability to store wave function, so to speak, hasn't improved dramatically, in the sense that from 3,000 years before the current era, we were able to store about 10 qubits using a piece of paper, essentially. And nowadays, because of this exponential complexity, maybe we can store 54 qubits, but it's clear that there is an exponential wall despite the improvement in the storage capability of the human race, if you want. However, I mean, the thing that we have to ask ourselves is whether this complexity is truly exponential, or if we can do something about it for physical systems, right? So this brings me to the notion of these corners, in the sense that, I mean, nominally, the wave function, so this object that underlines a lot of problems in quantum theory, lives in a huge Hilbert space, which is exponentially large and characterized by all the possible states. However, the key insight is that it is often the case that physical states are not the most general random, if you want, state in this Hilbert space, but they're characterized by symmetries. They have a lot of regularity properties that make them much more well-behaved than the random, if you want, state in Hilbert space. So this is a dramatic simplification because we can try to exploit these to describe physical states more efficiently. So the key question is then, however, how can we access these corners? So how can we describe these corners of Hilbert space efficiently? I mean, my personal point of view is that our best hope, if you want, our best shot at solving this problem is through the variational formulation of quantum mechanics. So essentially, I mean, you can hope to parameterize your wave function with millions possibly of parameters. So that's what I call here W in this parameterization. And, you know, because of the variational formulation, for example, if you're interested in solving a ground state problem, you can just, you know, minimize the energy and try to find somehow a description of this corner, which is induced by this specific parameterization, but which is still sufficiently expressive to describe a large part of this green region that I was talking about before. So in this talk, I will actually mostly concentrate on the left-hand side of this diagram, which is essentially using classical variational states that are inspired by machine learning. Okay, so and in this case, I mean, you will see that we will require a CPU, GPU, or TPUs if you have any of those available, but classical use processing units. I mean, towards the end, I will try to tell you also about other machine learning quantum variational states. So these instead require a QPU, so a quantum processing unit. If you have one, or if you can access actually one from Google or IBM, then this is your part of the story. Now, in general, I mean, how can we access these representations of Hilbert space? Well, historically, I mean, also especially in the context of condensed matter and nuclear theory, that I mean, strongly interconnected, but from this point of view, people have been devising variational states that are sufficiently flexible to describe some phenomena, like Jastrow states, Laughlin wave function, Pfaffians to describe pairing. So all these wave functions that rightly so carry the names of famous people are essentially some BCS wave functions, or are those wave functions with a few parameters, like tens at most, that describe the physics of important phenomena, but they describe a relatively small area of this green region in the sense that they are strongly tailored to describe some specific phenomena, for example, BCS wave functions. However, I mean, the situation has, I would say, quite radically changed with the introduction already of Med-explorer states in the 90s from Steve White, because there the idea was to somehow extend these wave functions to describe more general systems. For example, low entangled systems in one dimensions are very well described by what introduced, they are now known as Med-explorer states. So without going too much into the details, I guess most of you are familiar with this, but the idea is that here, instead of having just one or two variational parameters, we have a lot of them, which are essentially the entries of these matrices. And your wave function is a product of matrices. And increasing the size of these matrices, you can describe essentially to arbitrary accuracy one-dimensional systems. And these have a lot of very nice properties. And these ideas have been extended also to dimensions through, for example, PEPs especially. It's known that they describe a pretty large area, I mean, region of these green, if you want, region of physical states, especially area law states. However, I mean, it's also known that there are even area law states that are not efficiently described by tensor networks in two dimensions, for example. And it is also known that there is volume law states. So, for example, those that arise from the dynamics of quantum systems, or even from higher excited states, or even finite temperature calculations, those are typically not efficiently accessible by planar tensor networks with small one dimension. So these states are still, there's a lot of interest around those, but they have also some limitations. So the issue is then, how can we take somehow these ideas from tensor network, for example, and make them, extend them to, in a way that we can try to address maybe a larger fraction of this green region that we are interested in. So this is essentially the issue. So can we have a flexible answer which is also computationally efficient in a way that we can handle also volume law states, for example, more efficient. So this brings me to this idea of neural network states that we introduced in 2016-17. And the idea is essentially that you parameterize your wave function, so you have a variational formulation of your wave function in terms of a neural network. So a neural network, for those of you who are maybe not familiar with this, is essentially just a composition of linear and nonlinear functions. So for example, if you take a quantum system which has spin quantum numbers up to S1, Sn, so these are just the amplitudes, for example, of my wave functions, then you can write these amplitudes as a black box. So instead of storing them as you would do naively, you write a black box parameterized by some parameters, which is a neural network. And what this black box does is that it takes a linear combination of this vector of quantum numbers. So this is this W, those are weights. And then you compose these weights with a nonlinear function, this G, that typically is an hyperbolic tangent or other things. Then you compose again with a linear function, nonlinear, linear, nonlinear, until you reach the end of this black box, which will be the value, if you want, of your wave function. So this is nothing but a way to parameterize in a rather general and compact way a wave function using a sequence of L layers, and this is what people call a deep network. Okay? Now, some of the general properties of these wave functions, so these neural network states that we introduced, are summarized here. There's a lot more, but I won't discuss them. One, for example, you can represent essentially all known variational states that carry names of famous people, so Jastrow, Laughlin, etc. For example, Laughlin states for topological properties, those are efficiently written in terms of these neural network states, in the sense that you can find a neural network that has polynomially many parameters and that can describe these states efficiently. We have also some new results concerning the description of that MPS. We now know, this is still unpublished, but we now know that we can write MPS wave functions also with neural networks of polynomial sites. And I mean, especially, and this is part of the interest of these states, is that they also allow to describe volume law states. So again, for example, critical wave functions with a number of parameters which scales only with the essentially polynomially with the number of particles and not exponentially like for some tensor networks. So this is the context, for example, of this work, where we show that if you have a deep network, where they showed that if you have a deep network, you can represent efficiently volume law states. Now, I mean, during this talk, I will tell you a bit about some of the applications that we did, and I would like to emphasize that all these problems are self-learning. I mean, concerning the simulation of quantum systems, in the sense that we don't have a pre-solved Schrödinger equation that we try to learn, as in other applications. But here, the only input we have in this kind of applications is typically just the Hamiltonian. So if you want the fundamental ab initio quantity that you have in your theory. So we don't have pre-solved solutions. We really try to solve using these neural networks the problem from the start. So, and essentially, there is several applications, and all of them can be, I mean, including dynamics and dissipative dynamics. I won't talk about this, but if you want, we can talk later about this. But I mean, I will mostly concentrate on ground and excited states properties, where, I mean, the trick, I mean, as you know, is that we just rewrite the quantum expectation value as a statistical expectation value, as Macmillan taught us in the 60s with the variation of Monte Carlo. And this is essentially the key result that you get, because you can now obtain an expectation value of the Hamiltonian sampling from psi squared, so from the Born distribution, and average the local energy, which is this object which is defined for lattice Hamiltonians in this way. Okay? Then what we do, and which is again essentially identical to what people do in standard unsupervised machine learning, is that we form gradients of this loss function, so of the energy, and we measure these gradients from the samples that we generate typically using Monte Carlo at each time step, and then we use this gradient to reduce the energy. Okay, so this is standard stochastic gradient descent approach, which is very similar to other applications in deep learning. The technique at the end that we use to do this optimization is what has been introduced by Sandor Zorella, and he called stochastic reconfiguration. which is essentially identical, apart from some differences, small differences, to what had been introduced around the same time, a little bit before, in the community of machine learning that goes under the name of natural gradient. So the natural gradient essentially is this idea of using a preconditioning matrix, which is this Fisher information matrix in the context of probability distributions, which is a correlator of the gradients of the wave function, and that this is used to essentially, it is applied to the parameter updates and used to improve the Baire gradients G. And this is equivalent to, you can show, to solve your optimization problem in the metric, in the Riemannian metric induced by the variational parameters, instead of the Baire metric, which is just the Baire metric of the space. So this is typically much faster than doing the standard gradient descent, if you want it in this space. Now, I mean, just to give you an idea of the results that you can obtain with these approaches, a benchmark that we've used and also others have used in this field to somehow see how well these states can perform. Standard benchmark to some extent are frustrated two-dimensional speeds. So this is a model that arises in condensed matter. Essentially, for example, the J1, J2 model is a prototypical example of hard speed model that you can't solve exactly, for example, with tensor networks or with Monte Carlo, quantum Monte Carlo, because of the sign problem. So it's really an open problem where we don't know the exact ground state. Essentially, one of the questions that are still open for this model is whether there is a spin liquid phase that intervenes the two limits where J1, so this Heisenberg coupling in 1D in 2 dimensions among nearest neighbors, is dominant, and the case instead where J2, so the next to nearest neighbors coupling, is dominant. That gives rise to a striped order. So the question is whether in the middle, when J2 is comparable to J1, there is some disordered spin liquid phase that emerges. I mean, our approach to this problem is essentially to use a convolutional neural network, which is depicted here. So here, these filters, so these linear transformations that I introduced at the beginning, are taken to be short-ranged. So this is an important feature that is used to exploit the locality, if you want, of the problem. And then you stack a lot of these short-range filters until you reach the output, which is your variational state. A nice feature of this is that this wave function is automatically translational invariant, and you can also impose actually also other symmetries like reflections and rotations. Now, I mean, in the first work, we used essentially a version of this neural network with only one layer, which is an RBM, reciprocal Boltzmann machine, but where we used to increase the number of filters, so the width of this network, which in that work was called alpha. And you can see, I mean, this is the Heisenberg limit, and this is the error on the energy that already, I mean, playing with a very small and somehow very old-fashioned neural network with only one layer, you can already improve on some existing results of the time, for example, on PEPs at the time, and essentially the accuracy systematically can be improved. However, I mean, using these new results based on the convonets, so on this later architecture, we can further improve on this Heisenberg limit. And as I will show you in a second, we are at a point where we can further improve this, basically down here, and where we can exploit even better these convolutional states to find essentially this Heisenberg limit almost exactly this. So, but coming back to the original problem where we have also a finite J2, so the point that I was showing you before was J2 equals 0, so essentially here. These wave functions are essentially competitive and in some cases better than most other wave functions that have been used in the past 20 years on this problem. So for example, if you look at this plot, this is the energy difference between our approach, the CNN, convolutional neural networks, and some other wave function, for example, the MRG and the fermionic variational states. Essentially, so if these points are in the upper part, it means that our variational energies, which is the only thing we can compare among different methods, is lower than the other variational methods. Otherwise, we have that our NQS neural network quantum states has Schwarz energies. So you see that apart from I mean, a couple of, unfortunately, 2 points that are in the middle of this phase diagram, mostly and this was really the first application of this technique, but we already find an improvement, sometimes even substantial, over the other approaches that have been used to study this problem. So why do we have not? I mean, why we don't have the best energies, if you want, over the entire field? Well, I mean, these have been studied, and there are some conjectures. We are not sure yet about. I mean, there can be a lot of different factors, but one seemingly reasonable explanation is that, which has been studied in this paper, is that essentially the number of samples that you need to describe these frustrated states is typically very large, much larger, if you want, of the number of samples that you need in an ordered phase. So, for example, if you have an L ordered phase, right? So what they show here is the overlap. I mean, essentially, how accurate is your wave function, and it is accurate when it is 1 as a function of the number of samples. So this number is proportional to the number of samples. And they see on a similarly frustrated model that when you increase the frustration, there is essentially a sort of phase transition in the number of samples that you need in order to understand the ground state. And actually, in this case, actually, the larger J2, the more frustrated this model was. They saw clearly that the more frustrated, the more samples, critical number of samples you needed. So this might explain why we don't reach yet the state-of-the-art accuracy on these points, because we are somehow still a bit limited by the number of samples that we can afford during the sampling. However, I mean, this is the optimistic point of view on the story. It seems that the critical number of samples that you need to at least looking at relatively small systems, it's not dramatically increasing the system size. So this is the number of samples that you need to have a fidelity close to 1 as a function of the system size. So this is 20 spins, 36 spins, and this is the number of Hilbert number of Hilbert states. And you see that essentially the number of samples that you need is not increasing too dramatically when you go from 20 to 36. So it seems that this is not something we cannot fight, if you want, against in the near future. Okay, so this brings me maybe to another topic that I think it's quite maybe interesting also for applications in nuclear theory, which is this notion of computational tractability, a notion in the variational Monte Carlo which is not been exploited enough, in my opinion. So, but essentially, we define a variational wave function to be computationally tractable if it satisfies 2 properties, A and B. It is a very nice paper. So the first property is that you are able to sample from the Born distribution, from chi-square in polynomial time. And the second property is that you are able to return the coefficients, so psi of x, so if x now is your quantum vector of quantum numbers, also in polynomial time. So typically, these 2 conditions allow you to establish some theorems, for example, that guarantee that you can compute expectation values of observables, in this case A, or matrix elements even, in polynomial time. So why do I care about this? Well, I care about this because, I mean, if you think about it, actually, most of the variational wave functions that people have been using in condensed matter or even nuclear theory are not computationally tractable according to this definition. So, for example, if you consider Jastrow states, they are not computationally tractable, but even generic deep network states are not computationally tractable. So, why it is the case? Well, the reason is that essentially, for example, Jastrow states, you are not able to sample. I mean, at least in theory, in polynomial time from chi-square. So the reason is that when you do Markov chain, there's no guarantee that you will be able to sample from these states in polynomial time, because you might have some very long correlation times, or you might have some metastable states that will prevent you to sample in polynomial time. So this is essentially the notion that is violated by most quantum states that we use normally in many body theory. Our idea was to somehow lift this limitation and introduce, extend an idea which is already used in the context of generative learning, so in machine learning, and it is what we call autoregressive quantum states. And essentially, the idea is that you write your variational states as a product of what we can call conditional wave functions. So these conditional wave functions are such that the psi I, in this case, is a function that depends only on the previous values of the quantum numbers and not on the subsequent ones. So this is what is called an autoregressive structure. And also we impose that these conditions are normalized in L2 norm. Okay, so in turn, this guarantees you that the full wave function is exactly normalized to 1, which is something that you typically don't have with other parameterizations. And it also allows you to perform exact sampling. So essentially, you completely remove Markov chain in the variational Monte Carlo step, if you want, when you do this learning loop. So in practice, I mean, we use for these convolutional states some specific networks. I'm not going into the details, but I will be happy to discuss about this later. So one is called Pixel CNN, Pixel Convolutional Neural Networks, and those are essentially some special filters. So these are still convolutional state networks, but with some filters that are 0 in some specific positions that guarantee this condition, so this autoregressive condition. And the moral of the story is that we can exact sampling because you can sample one spin or one particle at a time without doing Markov chain, and there is 0 autocorrelation times, and there is 0 need to essentially craft and tailor new Monte Carlo moves every time you have a new system. So this is completely automatic. Now, I mean, we care about that also because we can implement these wave functions more efficiently, for example, in a GPU. And in this paper, for the first time, we were able to use these wave functions with about 1 million parameters and depth 20 to study these spin problems, which was not possible with standard deep networks when you do Markov chain Monte Carlo. And this sampling pays off because you get also better accuracies. So this is the transfer speed Asimov in 2 dimensions. And you see that if you do this direct sampling, so these green lines, also the error you get on the energy is much better than what you get doing Markov chain. This is a situation where you have ferromagnetic domains. And of course, I mean, if you started doing a clever Markov chain where you have block moves, you could also get down here. But the point is that the neural network doesn't know about that. It automatically finds, in a sense, this efficient way of sampling from the wave function. Okay, so, and I mean, as the result I promised you earlier is that also on the Heisenberg model, essentially we are now, I mean, in the 10 to the minus 5 using this autoregressive technique that allows us to sample efficiently also from, let's say, more complicated models like the Heisenberg. Yeah, unfortunately, I don't have much time about to discuss about fermions, but I know that Alessandro will tell you more about that and also applications to nuclear theory. But I wanted to just flash you maybe the applications to quantum variational states. So essentially, states that are not implemented on a classical computer, like the ones that we've seen until now, like neural networks on a GPU, but those are states that are implemented on a QPU, so on a quantum computer. So, and also because this is part of the topics of this conference. And I mean, the idea here is that instead of using a neural network with a lot of layers, you use a quantum circuit with a lot of layers, where each layer is parameterized by some unitary, and overall your quantum circuit is a sequence of unitaries that is parametric in a lot of parameters that I call here theta. And essentially, you can think of the VQE, so this variational quantum eigensolver approach, as a variational Monte Carlo run on a quantum machine, in the sense that you can prepare a state, psi theta, which is the application of this unitary to some trivial initial state, and then you can measure, this time not doing Monte Carlo, but really just applying if you want, the Hamiltonian, doing the projective measurements of your quantum computer, the energy as a function of theta. Okay? So this can be done efficiently, typically for many Hamiltonians. For quantum chemistry, it's a different story, but that's not going to that. But I mean, typically you can do that. The point is that we showed that actually that there is a strong connection between the variational Monte Carlo world and this VQE world. And the key, I think, point is this, this quantity that I discussed before in the context of the natural gradient, which is this quantum geometric tensor, so this S matrix. And that arises naturally, so down here, so in the classical world, if you want, stochastic reconfiguration, natural gradient in machine learning, and also time-dependent variational Monte Carlo when you do dynamics. But the same quantity can be estimated also on the quantum computer and gives rise to other techniques, other approaches, including, for example, quantum variational imaginary time evolution, which is essentially what you do with VQE, and other applications. So, and we show that if you have a good way of estimating this object, you can also again, which is this matrix here, you can also you can also improve on the optimization on these variational applications on the quantum hardware, and I think this is crucial, interesting for also the interplay of these two fields, so classical variational techniques and quantum variational techniques. So if you are interested about the details of our quantum approach, you can find them in this paper. But I mean, just to tell you that, I mean, for example, if you compare, if you do this VQE on some circuits, you can see that if you use this quantum natural gradient, so which is this approach preconditioned by this S matrix, you can converge much faster than using just vanilla gradient descent. That we observe in the classical world, so this is not too surprising, but I mean, it's nice that we can also improve the quantum techniques using ideas from the classical. Okay, now I finished and I will tell you just one word about our open source project. It's called NetCat, and it's a way to run some of these simulations, especially on quantum spins, quantum spin problems. It's entirely written in Python, and if you're interested to collaborate, even just go here or on GitHub, and you will find all the details about this project, some tutorials. We are now in the phase actually of releasing a new version of NetCat, which is the 3.0 release, which was crucially removed actually the entire C++ code base in favor of a pure Python code base based on mostly on JAX, which is somehow a neural network deep learning framework developed by Google. And quite amazingly, I mean, with JAX, we managed to also get a lot of speed ups also on GPUs, which is non-trivial if you do variational Monte Carlo, also on sampling and not only on gradients. So this is a bit technical, but if you are interested in using these approaches to your favorite quantum problems, you should definitely look into what we've done and maybe extend it to your problem. Okay, so so one of the things that I actually didn't discuss, but I think that it's quite important. It's essentially this issue of optimizing also the phase and the amplitude of the wave function, and actually how many samples you need to learn the wave functions. So these are all key open problems that we are in the process of addressing, but where we need also input from other fields. So essentially the way we use to parameterize the wave function, which is a complex object, is still not optimal. In my opinion, there's a lot to be done in terms of how we parameterize on neural networks the sign or the phase of the wave function with respect to what is done in the standard applications. And also something which is non-trivial is how to exploit locality efficiently in these problems. So for example, if you have short-range interactions, you also want your model to have these short-range features incorporated in your problem. And also symmetries is something which is extremely important in this business, essentially, of neural network quantum states. And certainly fermions is the most important symmetry that is just being studied these days. I would say we are still in a heroic phase, so we are still at the beginning of the old developments, and there's a lot of to be done also, I think, in nuclear theory in this respect. So thank you, and I would be now happy to have a discussion.
Thank you so much, Giuseppe, for this very nice and interesting talk. and also being on time. So we have time now for questions. And if you do, you could either raise your hand or put it in the chat box. Let's see. Okay, so we have a question from Denis Lucas. So
yeah, nice talk. Do you hear me? Yeah.
Yeah, I can. Yeah.
Okay. On the first part of your talk, when you replace the wave function by a neural network, normally I suspect that you need to train the network. So
that's correct. Yeah.
Well, so does it mean that you need to have the exact solution in some cases to be efficient for other cases?
No, yeah, that was the point I was making here. So essentially, this is a self-learning approach. So we don't need a pre-solved Schrödinger equation, and this is quite crucial, I believe, for the development of this field, in the sense that we don't need somebody who has already solved the problem. Otherwise, this would be to some extent trivial. But what we do, our only input is the Hamiltonian. Okay. So our only input is the Hamiltonian, and then we essentially compute expectation values of the Hamiltonian over our variational states for some fixed set of parameters. We measure also the gradient of this object with respect to the parameters, W, and then we feed back the neural network and we change the parameters in the neural network in this way. Okay? So if you are familiar with reinforcement learning and unsupervised learning, so this is to some extent similar to what is done in that context. In the sense that you don't have pre-solved the problem, but you have to play against yourself if you want to improve your solution. And this is exactly what we do here, because our playing against ourselves means that we have to sample or generate new states from our wave function at fixed weights, measure this object, which is local energy, and then updates the weight and regenerate new samples. So we generate ourselves the samples. We don't have external samples. Yeah.
Okay, and how do you know that you are not in a local minimum?
Well, I mean, this is a standard problem in deep learning, and nobody knows. But the thing is that the gradient that you use is typically noisy enough that you can see this optimization problem as a noisy Langevin essentially dynamics. So where you have the gradient plus some noise, which is essentially equivalent to some effective temperature. And this effective temperature is, you can show it's essentially equivalent to doing simulated annealing in this space of parameters. So you don't know that you are in a local minimum, but this noise allows you typically to escape this local minimum.
Okay, thank you.
Okay, so we have a question from Morten in the chat box here. So have you, I can read the question here. Have you compared Boltzmann machines and neural networks on the same quantum mechanical problem? And if, what is your experience?
Yes, so the experience is that, it's here actually, let's see it in full glory here. But so essentially, yes. So okay. So these points are the restricted Boltzmann machines. So these one-layer networks, which are a bit obsolete, but nice to work with because they are simple neural networks, and we can often find analytic properties of these states more easily than with deep networks. But I mean, in general, yes. So the RBMs, which again are these points here, for example, for this problem, this is the Eisenberg model. Typically are good, but not. I mean, you can't push them to essentially the exact solution. Our experience is that using instead deeper network instead of wider network is more efficient, and this is the same that people find also in standard deep learning applications. You see that the difference between an RBM, so this point, and an actually deep network is almost two orders of magnitude in accuracy. So if you can actually exploit, I mean, this is not always the case actually, but if you can exploit the depth, typically this is worth it. Yeah.
Right. So that you know the exact answer to that, right? So it kind of guides you. How do you, if you don't have let's say full CI results or exact solution, how do you know you systematically approach that limit? Or how do you know why you should?
Well, I mean, all results are variational. So if your energy is lower, you are certainly improving on other results that you have. Mm-hmm. So let's say that the standard approach here would be that you increase the depth of your network, for example. You take that as a control parameter, and you will see your energy going down, right? With the depth of the network, then, I mean, as all variational techniques, there is no guarantee that you are not stuck into an excited state with zero variance, for example, in the local energy, but essentially there's no other technique that can solve this problem. In the sense that if you were able to find the ground state exactly of an arbitrary Hamiltonian, it would solve NPR problems, which is unlikely.
Okay, so Thomas I have a question here. Thomas Hoppenbrock, so he is asking, which previously unsolvable problems have been solved by CNNs?
You mean in the context of quantum applications? Well, yeah. So I mean, I just gave you an example of these of applications to this J1, J2 model, where essentially, I was telling you that there is this phase in the middle that we still don't know what's going on. And we are at the point, I believe, where we are close to solving the problem, but I mean, not quite there. But before solving the problem, we have to find the best energies essentially over all the regime here. There is some things that, I mean, this is from last year, so there's still a lot of work going on, and the people have worked on this for 20 years. We will be able to solve this in the next couple of years. So this is the answer to that question. But again, this is a benchmark, and you can see that you can perform better than other versions.
Mm-hmm. Let's see, and I don't know who was first there. Alessandro Lovato, if you want to go first, you raise your hand.
Yeah, so if you have like the same number of nodes for a shallow neural net, say a restricted Boltzmann machine and a deep neural net, why is it obvious that a deep neural net gives you better answer? Like, is it like a training issue that it's easier to train, or it's because
so this is not at all obvious actually, and I mean, the only, if you want, the theorems that we have on this, it's what I showed here. So essentially, I mean, this is a hint if you want, but they show that if you have a deep network with short range weights, so like a COMNET, this is more efficient in terms of weights with respect to represent a volume state, so long range correlation, for example, with respect to the equivalent one layer network, but with long range weights. So you see. So this is the only, rigorous statement that we have on the separation between a wide or deeper network. In practice, my feeling, I mean, my opinion is shared by many others, is that these deep networks are much easier to train because they have shorter range filters. So they exploit a bit better the locality of the problem. Instead, if you have one layer, but with long range filters, these are much harder to train because they essentially couple everything with everything at the same level. So this is much harder to train.
Okay, thank you.
Okay, so we have one more question here before we go on to next talk. Luis Robledo is asking how complex is the evaluation of the energy with QNN as compared to more traditional approaches?
So QNN, I assume that you mean quantum neural networks. Is that correct, Luis? I mean, on the quantum computer, right? Well, I mean, I go with that assumption. I mean, and
I would have to go with that assumption as well. Yes, he says yes.
So how complex is the evaluation of the energy? That's a good point. So the main bottleneck with QNNs is that if you have for example, a quantum chemistry Hamiltonians, you have to, the main difference is that in the quantum case, to estimate the energy, you have to estimate the energy of each of the terms in the Hamiltonian. And typically this is, I mean, one by one. Whereas in the classical case, so in quantum Monte Carlo, variational Monte Carlo, you can estimate them all at once. So typically, and this is a serious drawback actually, you need, if you want to have a precision on the energy, I mean, just in terms of statistical precision, which is of the order of chemical accuracy, you need a number of samples, which is gigantic even for small molecules. So if you have, let's say, H2 and you want a chemical accuracy, you need to perform something like 10 to the 6 or 10 to the 7 measurements on your hardware, which is not always something feasible. And this is only H2. So if you go, from to a larger molecule, the number of measurements will scale much more dramatically. So this is a serious problem in the VQE space, which is not discussed very often, unfortunately, but this is the main difference with respect to the classical approach. You don't have the zero variance property for the experts in the audience.
Mm-hmm. Okay, thank you, Giuseppe, for this very interesting discussion and talk.
Thank you.
I think we are actually right on time. So moving to the next speaker of this session here, Alessandro Lovato. So
yeah, let me share the screen.
And he will be talking about neural network quantum states for atomic nuclei. So please, during the talk, you could add questions to the chat box. And also after, there will be a 10-15 minute discussion where you can also raise your hand for asking questions.
Oh, sorry.
So with that, Ala, please go ahead.
Can you see the screen?
Yep.
The talk? Okay, good. So thank you for the invitation. And yeah, I'd like to take on what Giuseppe has just said and expand a little bit the discussion. I mean, wonderful discussion in the domain of nuclear physics. And before doing so, I'd like to remind you the grand challenge that we are facing now. And basically, we want to describe atomic nuclei as they emerge from the individual interactions among protons and neutrons. And we developed these interactions starting within effective field theories of QCD. And these effective field theories exploit the separation between the hard scale and the soft scale. The hard scale is typically the nucleon mass, the soft scale is the exchanged momentum. And if you believe in this separation, and you can write down a Hamiltonian and assume that nucleons, and you can assume that nucleons can be treated as point-like particles, and they interact, and then the Hamiltonian is a non-relativistic one with the kinetic energy, a two-body potential, and a three-body potential. And again, in contrast, if you wish, to condensed matter problem, here we are not aiming at per mil or even better accuracy, just because our Hamiltonian is not exactly known. So this Hamiltonian comes with an intrinsic theoretical uncertainty. So our many-body method has to be accurate, but maybe not as accurate as the one typically used in condensed matter systems. Let me give you first a brief overview on conventional, if you wish, continuum nuclear quantum Monte Carlo methods and the challenges they face in describing nuclei larger than carbon-12, say, and why they're facing these challenges. So to echo Giuseppe's presentation, suppose that we start from a variational Monte Carlo wave function in nuclear physics. And this is typically built using adjuster ansatz. So we start from this phi, which is a mean field wave function, or like that's equivalent, for example, to the reference state in a couple cluster approach. And there are no correlations except the Pauli principle here. And then we act on top of it with spin-dependent two-body correlations and spin-dependent three-body correlations. In principle, there are more. So this is an ansatz, there is a truncation here. But this ansatz has been proven to be accurate to describe nuclei up to carbon-12. And like in the neural network case, the best variational parameters of this wave function are found exploiting the variational principle. So we change these parameters to minimize the expectation value of this Hamiltonian on this trial wave function. Now, in conventional quantum Monte Carlo approaches, one writes down the spin-isospin-dependent correlations in a way that's consistent with the potential. So if the potential has a strong short-range repulsive core, like for the argon class potentials, for example, then you expect this Jastrow function to be small at small interparticle distances. So just because the probability of two nucleons to get close to each other must be small if the repulsive core is strong. And on the other hand, we write down the three-body correlation usually, excuse me, in a perturbative fashion. So basically, we expand the three-body potential, and we parameterize the three-body correlation like that. Now, these wave functions are accurate, but they're not exact. And we use them as a starting point usually to perform imaginary time diffusion techniques. And since any trial wave function can be expanded on the eigenstates of the starting Hamiltonian, one can easily show that in the limit of large imaginary time, when the imaginary time evolution operator is applied, only the ground state component of the initial trial wave function survives. And here, this is an example of early calculation of the helium-4. So as tau increases, the energy converges to the exact ground state energy of that given Hamiltonian. And again, typically there is a more than % error on the Hamiltonian. So a % level accuracy on the many-body method is more than enough for our purposes. Now, why do quantum Monte Carlo techniques exhibit this unfavorable exponential scaling? Well, the reason is the following. During our imaginary time propagation, we apply the exponential of the Hamiltonian from one spin state S to the next spin state S prime, and we sum over all possible spin-isospin combinations. In the Green's function Monte Carlo method, we sum over them rather than sampling them, and I'll come back on the issue that comes about when you try to sample them. Anyway, the idea is that pretty much as what Giuseppe said, if you have a three-body system and you only consider the spin, for nuclear systems, we also have the isospin, so the array will be even larger. We already have 8 spin combinations. So it's clear that the exponential scales like 2 to the A for the spin, and for the isospin, it's a little bit better just because charge is conserved. So you don't, if you start from a state with, say, a proton and 2 neutrons, you never end up with a state with 2 protons and 1 neutron. But still, one can show that the scaling is basically exponential, and this effectively limits the application of this method to carbon-12. Now with the GPUs and supercomputer, we are going to expand it to 13 and 14, but we are not going to get anywhere near to, say, oxygen or even medium mass nuclei, say, calcium. Okay, so the natural question to ask is, okay, why don't we sample the spin and the isospin degrees of freedom? And this is exactly what the auxiliary field diffusion Monte Carlo methods does. So you write your many-body spin state, if you want, as a product, as an external product of single particle spinors. And so instead of having 2 to the A coordinates or amplitudes, if you want, you only have 4 times A. But of course, you pay a price. And the price that you pay is that basically a given spin-isospin configuration is basically not entangled. And what you do, you sample the entanglement in the imaginary time propagation. So to do that, what does create, why is entanglement there? Entanglement is there because there are quadratic spin operators in the nuclear Hamiltonian, say sigma I, sigma j. And what we do, we linearize them using Hubbard-Satanovich transformation. So if you have a quadratic operator, you can sample the auxiliary field X and write it as a one-body operator. So what happens is that each spinor during the imaginary time evolution is rotated. So you start from a set of 4 A numbers, and then you apply the potential, you sample X, and you end up with a set of rotated spinors. But these are still single particle ones. So to get the entanglement associated with the, with the nuclear Hamiltonian, you need to average over them when you compute the expectation value. All right, so it looks like this method works, and in fact it's working, but there is a drawback. So this method in principle scales polynomially with the number of nucleons, but it's somehow limited to simplified potential. And the answer, and why? Well, the problem is that even for a single spin-isospin configuration, when you compute the energy expectation value, you're still facing an exponentially scaling complex problem. So the trial wave function that we're using in full glory is the symmetrized product of 2 body adjuster operator that are spin dependent applied to an independent particle state. So suppose for simplicity that we only have a central channel and a spin dependent channel with a quadratic spin operator, so sigma I, sigma j. And sigma I, sigma j can be written as twice the spin exchange minus 1. So now let's apply say you have 3 particles, and we apply this correlation operator. Forget about the symmetrization operator here, but even if we want to apply this product of 3 correlation pairs on a single spin state, S1, S2, S3, we immediately see that once we apply F23 and F23 sigma 1,3, we obtain 2 different single particle spin states starting from 1. Then we apply again, and we obtain 4. And then if we apply again now the 1-2 correlation, we get 8. So basically, even if you sample the spin and the isospin, when you evaluate the trial wave function and you compute the energy expectation value, you still require a number of operations that scale exponentially with the number of particles. Now, in principle, you can use simplified trial wave functions, because the whole point of the imaginary time diffusion is to give you the exact energy, no matter what your trial wave function is. The problem though is the sign problem. So the trial wave function is crucial in controlling the sign problem. So the fact that we are dealing with fermions and not bosons. So the ground state of the fermionic system is in fact an excited state of the bosonic theory. And if you leave the imaginary time evolution to its job, basically we're going to converge to the bosonic ground state. And what the trial wave function does, it singles out the fermionic component of this bosonic wave function and projects it to the fermionic state. So it's important to have accurate trial wave function, and apparently to have them, you need an exponentially large number of operations. So like now in conventional quantum Monte Carlo methods, what we do, we linearize the correlation operator. So instead of retaining the full complexity of the spin-dependent correlations, we just linearize them. And in this case, instead of having an exponential scaling, we have a polynomial scaling, but we lose one of the key properties of any quantum mechanical wave function, which is factorization. So this wave function, for example, does not factorize. So if you take 2 subsets of nucleons in your nucleus, and you take them far away from each other, your resulting final wave function cannot be written as a product of the 2. So this is still a variational wave function, but it's not expected to be accurate for large nuclear systems. So that's why we cannot use it for nuclei larger than oxygen-16. But for oxygen-16, here, Diego Nardoni, Stefan, and collaborators obtain very nice results with this wave function. But we would like to go beyond that. Now, another exponentially difficult problem faced by conventional quantum Monte Carlo is imaginary is studying response function. So the real-time evolution of the system, which is relevant, for example, to describe electron and neutrino scattering experiment. And all the information on nuclear dynamics is encoded in these response functions, which basically describe the transition from the ground state of the system, site 0, to the final state, and you have an energy conserving delta function. These are intrinsically dynamical properties. So what we do in quantum Monte Carlo is basically, instead of computing all of this transition amplitude, we study integral properties of the response function. So basically, instead of computing this black line directly, we compute the integral of this black curve weighted by the Laplace exponential, e to the minus omega tau. And the way this is done basically is that we start from the ground state of the system, we apply the current operators that we have a mixture of excited state, and we try to understand what this admixture is by cooling the system down. And this is, of course, if this is the starting response function, this is our Euclidean response. And basically the goal is to go back from the Euclidean response that we compute with quantum Monte Carlo to the response function. Of course, this is the ideal battleground, if you want, for quantum computation, because quantum computers are ideally suited to do real-time evolution in principle. Here, what we do, instead of doing a real-time evolution, we do an evolution in imaginary time, and then we do an analytic continuation procedure to go back to the real time. So what is the problem? The problem is that since these Euclidean responses come with errors, there are many, many response functions that are compatible with the starting Euclidean response within uncertainty. This is eventually related to the fact that the Laplace operator is a smoothing operator. So we typically use maximum entropy techniques, and we find them reliable enough for quasi-elastic responses, but they fail somehow to reproduce the low energy structure of the response function because this is related to the high imaginary time propagation. However, I mean, we did this, and we did this for electron, for neutrinos, and we recently found, I mean, this enhancement of two-body currents that are needed to explain, neutrino oscillation data from the Minimun and T2K experiments. But what we want to do, we want to go beyond carbon, we want to study oxygen-16 and argon-40. And if we apply, say, the auxiliary field diffusion Monte Carlo, we're going to have higher noise level in the Euclidean responses, non-negligible, no low energy transitions here. So we need to go beyond maximum entropy. And in the past, there have been many works that have demonstrated that machine learning approaches are suitable for tackling this inverse problem. So you're faced with a noisy input, and then you want to reconstruct the response from that noisy input. And in Krishnenstock, this will be explained in detail, but I mean, just to flesh it out here, we propose a physics-inspired artificial neural network, which is able to approximate the inverse of the Laplace transform of nuclear electromagnetic response functions. So what we did, we produced a set of synthetic data for responses characterized by 1 peak and 2 peaks. And we train our neural network on this synthetic data. And then we gave the net like a set of data that the net had never seen before. And we see how the net performs and compare with maximum entropy. So for the 1 peak case, maximum entropy does a good job. So it's the green. The neural net is the orange, and the original response, we knew the answer in this case, is the blue. And the physics neural network outperforms maximum entropy, but maximum entropy does a good job here. However, in the 2 peak case, so when responses are characterized by a large quasi-elastic peak and then some low energy transition, we see that the neural net really outperforms maximum entropy in reconstructing the low energy behavior of the response function. However, all the details of this approach will be given in Krishnenstock. Now let me switch to the main part of the talk, which is how we are trying to use neural network quantum states to describe the wave function of the atomic nucleus. So of course, I mean, we have been heavily inspired by work done in condensed matter system, especially by works from Giuseppe. And they demonstrated that even relatively simple neural networks like restricted Boltzmann machines can efficiently represent the wave function of spin states, and they can in fact beat like typically commonly used variational ansatz. And the application to the continuum and to field body systems followed shortly thereafter. So in this case, the input of the net was like a discrete set of spin states, and the output was the wave function. Here in field body system application, the input is the position of the particles in the continuum, and the output is again the wave function. In nuclear physics, somehow we're faced to a problem which combines the two, because the coordinates somehow are in the continuum and the spin are discrete. Okay, so the problem is somehow challenging. So we started, and we were not the first, of course, to face this problem. There is very nice work from James Kibble and Arnau, and James is going to talk next. And they actually, they were pioneers in this, in the sense that they devised the first neural net, the first variational representation of the variational state of an atomic nucleus based on neural network. And they fully solved the deuteron in momentum space, including both the S and the D state, using the sophisticated N3LO Entame-McLeod-Carrel-EFT nucleon-nucleon interaction. And the parameters of the neural net, so the weight and the biases of the network, are optimized by minimizing the variational energy using the RMS-prop method. As you can see, you start from this value of the energy. We know what the exact solution is. And then after hundreds of thousands of iterations, you get basically the same value of the energy. What we did, we took a slightly different point of view. So I'm a fan of the coordinate space representation. So we decided somehow to stick to it. And we considered the leading order pi-on-less CFT Carrel Hamiltonian, which includes a 3-body force. So this is we thought of it as a prototypal problem for nuclear physics applications, because we typically have a 2- and a 3-body force, and there is a spin-dependent interaction. So as I said, to fully tackle the problem, in principle, we should represent both the spin isospin and coordinate space amplitudes of the wave function on a neural net. But to begin with, we said, okay, why don't we start from an artificial neural network representation of the Jastrow function? So we assume that our variational state is a many-body Jastrow function, correlation operator, times a mean field state. So the antisymmetry of the wave function is encoded in the phi, and the Jastrow is a symmetric function of the coordinates. And this is a more general ansatz than standard product of 2 and 3 body Jastrow terms, because here all particles are correlated. Here instead, this correlation is assumed to factorize in a product of 2 body correlations and approximated 3 body correlations. Now here we consider the deuteron, helium-3, and helium-4. So for these S-shell nuclei, like in the very early application of variational Monte Carlo techniques, we assume that the mean field part only depends upon the spin and isospin degrees of freedom. So for the deuteron, for example, we have a proton up and a neutron up. And if we assume that, since the Jastrow does not depend on the spin, when we act with sigma 1, 2 on the wave function, we get just the same one. And on repeating the same argument for helium-3 and for Triton, the sigma 1, 2 is -1 and -1. So basically, this is a scalar problem, but still, it's a scalar problem even if we consider these ansatz with the 2 and 3 body Jastrow terms. And this is how our artificial neural network looks like. So we considered 4 fully connected layers. And the first layer basically is the input one, and we give the net as input the position of the nucleons, X, Y, and Z for all the nucleons. So basically it's 3A. And these positions are basically already, the center of mass coordinate is already subtracted by these coordinates so that we automatically remove center of mass contaminations from the kinetic energy. And then we have 2 additional fully connected layers, and finally the output one. And since we are working in coordinate space and we need to compute the derivatives of the wave function with respect to the coordinates, we cannot use the ReLU activation function, but we need to use differentiable soft plus activation functions. And also, so this wave function does not only serve as a wave function to compute the energy, but it also guides the metropolis walk in coordinate space. So basically, if these weights and biases are randomly initialized, this wave function does not confine the walkers in a finite space. So what we do, we add a Gaussian function to effectively confine the nucleons within a finite volume. Now, what happens, hopefully, our hope was that, okay, because of the representation theorem, this U can represent any function in principle, so it will compensate for this harmonic oscillator trapping and eventually give rise to the correct asymptotic tail. So how did we train the net? Well, we had a total of 18,000 trainable parameters, and pretty much in line with standard variational Monte Carlo techniques, we trained them by minimizing the energy expectation value, so the expectation value of the Hamiltonian on this variational state. So typically, stochastic gradient descent methods rely on the gradient of this energy with respect to the variational parameters, so this GI. However, what we did, we used, as Giuseppe mentioned, a preconditioner based on quantum Fisher information, which is basically equivalent to the stochastic reconfiguration method. So we supplement the gradient with this overlap matrix S, which is both the gradient and this matrix S are covariance metrics, so that even if you use a finite number of Monte Carlo samples, their errors are much lower than pure expectation values. And this is our update rule. So the parameters at step S1, S+1 are the parameters at step S minus the learning rate, eta. But instead of the gradient, we have this preconditioner here, which greatly improves the convergence of the method. So here I'm showing the, excuse me, the convergence pattern of the deuteron binding energy as a function of the stochastic configuration iteration. And as you can see, already after 1,200 iteration, we get the exact ground state energy. And this has to be compared to the hundreds of thousands of iterations that are needed using a simple stochastic gradient descent, even if supplemented by more state-of-the-art optimization protocol, such as RMSprop of Adam. Stochastic reconfiguration really has really proven to be efficient. The bottleneck here, on the other hand, is that we need to compute the Jacobian, and Jacobian calculation in PyTorch is not as efficient as one would hope. So there are tricks to overcome this difficulty, and one of them requires a lot of memory. The other one is basically would require major changes in PyTorch for switching to a different computational environment, for example, JAX or TensorFlow. But these are technical aspects of the problem. But there is a price that we need to pay to compute these metrics. And these are the results that we obtain. So for the deuteron, we basically obtain the exact answer, fully consistent with the Green's function Monte Carlo calculations. For triton instead, we do consistent with the standard variational Monte Carlo ansatz, slightly better, but we do worse than the Green's function Monte Carlo calculation. Why? Because we are neglecting spin-dependent correlations. So if we were to do a Green's function Monte Carlo calculation without spin-dependent correlations, then we get the same result as the variational neural network. And for helium-4, the situation is even, it's clear as well. So we do better than standard variational Jastrow ansatz by 0.2 or 0.6 MeV in this case, 0.5 MeV, but we do worse than the full Green's function Monte Carlo calculation because again, we're neglecting spin-dependent correlations basically. But our results are consistent with Green's function Monte Carlo calculations when spin-dependent correlations are neglected. And in addition to binding energies, we also show results for single nucleon densities. Here I'm showing Triton and helium-4 compared to the GFMC. So the orange is the artificial neural network and the blue is the GFMC. The agreement is excellent, not only in the short distance part, not only at short distances, but also in the slowly decaying exponential tails. And this is a proof that the neural net learns how to compensate this harmonic oscillator trapping function and reproduce the exponential decaying tail, which is notoriously difficult to reproduce using methods based on, say, harmonic oscillator expansion. Okay, so what are we doing now? Well, we are now even improving the convergence of the training, combining the stochastic reconfiguration method with state-of-the-art optimization methods, developed in machine learning approaches. So the idea is that in machine learning approaches rely on the gradient, and then they play trick with the gradients. Say they record the history of the gradients to try to construct approximated Hessian and things on that line. What we have to do, we have to replace the gradient with our modified gradient, which includes the display conditioner. And as a first example, we have considered the momentum method, which typically greatly helps accelerating the stochastic gradient descent in the relevant direction and dampens oscillation. So the idea here is that it's like a ball that goes, down. And what happens is that if you have like rocks on the side, if you follow the gradient, you might as well, do a zigzag before going down to the minimum. And instead with the momentum, basically, instead of updating the parameters with the gradient at step S, your velocity is not just the gradient at step S, but you also have some friction gamma times the velocity that you had before. So you somehow remember what your speed was before the next update. And that improves consistently the convergence in standard machine learning applications. And implementing that like out of the box, we have already achieved a 10-fold speed up in the convergence. And we plan to test also RMSprop and Adam that are even faster, optimization and more reliable optimization methods used by the machine learning communities. And we hope that this convergence improves even better. But now, the great challenge is, of course, how to include isospin-dependent correlations. So far, they've been basically neglected. And to do that, we need to consider a generalized coordinate X, which represents the three-dimensional position of the nucleon, the spin projection on the z-axis S, and the isospin projection on the z-axis T. Now, we want a fully anti-symmetric wave function, so if we exchange two nucleons, we need to get a minus sign, for example. And the way of doing that is using a generalized backflow. So basically, you write your wave function as a Slater determinant, but instead of using single particle orbitals, so functions that are function of a single coordinate X, these orbitals are function of all generalized coordinates of the nucleons. But the key point is that these functions phi must be symmetric under the interchange of xj, say, if this is x1 and then x2, x3, this has to be symmetric under the exchange of x2 and x3 for this determinant to be anti-symmetric. So we need to find a way of constructing permutation invariant function. And now we are using the deep set architecture. And it works like this. Of course, it is generalized to the complex case. It works like this. So you start from a vector x in Rm, And you want a function that is permutation invariant. So if you exchange x1 with x2, the final result doesn't change. So in the deep set, this original space is expanded in a latent space, which has a higher dimension, n times m. And then a sum is applied in this latent space so that the order of the initial inputs is destroyed. And then another net is applied to this sum to provide the function. And this function, it can be proven that if the size of the latent space n is larger than m plus 1, this f is, the representation theorem holds. This f can represent any permutation invariant function of x1 and xn. So this is basically what we are doing right now to encode spin-dependent correlations. Now, I'd like to give some perspectives before concluding. So our goal is to devise accurate wave functions for medium mass nuclei, which are otherwise inaccessible by conventional nuclear quantum Monte Carlo methods. And the shift of perspective here is that usually we provide momentum distribution, single nucleon densities, transition amplitudes. In this case, we will be able to provide to the community compact representations that are of the wave function itself in terms of the parameters of the net that are convenient for both theory and experiment, that are useful for both theory and experimental communities. Another point is that artificial neural network allows to study properties of excited states. And this is a central task and non-trivial challenge for nuclear many-body methods, especially for nuclear quantum Monte Carlo methods. They're really best suited to study ground state properties. And the dream, of course, is to do a real-time evolution. And in principle, artificial neural network can be extended to solve the time-dependent Schrödinger equation. And this is similar in spirit to the time-dependent variational Monte Carlo method. In this case, the distance to be minimized is this one, which is the difference between the time derivative of the wave function parameterized in terms of an artificial neural network minus the generator of the imaginary time evolution, which is the Hamiltonian. So this amounts in in minimizing at each time step this distance. And this involves non-trivial difficulties that are technical, but I'm happy to discuss them, and Giuseppe is the expert on this. But the idea is that if we manage to solve this problem, then we can do response function calculations. And there is a nice interplay with all the quantum computing efforts that is led by Alessandro, Joe, and the other Alessandro, for example, in nuclear physics. So this is the summary of the talk. We have developed a noise-resilient machine learning-based protocol for inverting the Laplace transform, and Krishnan is gonna go into the details of this approach in his talk. And we found that this method is more accurate than maximum entropy, especially in the low energy transfer region. So it allows to reconstruct low omega transitions. And it's resilient to noise in the input Euclidean responses. So to use maximum entropy, we need to use a lot of computing time to get extremely accurate Euclidean response functions. On the other hand, this machine learning-based approach seems to be much more resilient to noise. So it could be used in combination with the auxiliary field diffusion Monte Carlo method to compute the response function of larger nuclei, say oxygen 16, for example. But it's also applicable to other integral transform, including the Lorentz and the Gauss. And the Lorentz has important applications with Cabot cluster method, and the Gauss instead, it's going to be used in quantum computing applications. We obtained encouraging results with artificial neural network representation of the nuclear variational state. And we found that these representations outperform existing 2- and 3-body just raw ansatz. And using the stochastic reconfiguration method enables relatively fast training, and this convergence is further improved when used in combination with the state-of-the-art machine learning optimization methods like Momentum or Adam, for example, or MSProp. And we find a correct exponential behavior of single particle densities, including the slowly decaying tail, which is a kind of surprising in a sense, because this tail is not much sensitive to the energy. But the artificial neural net learns to reproduce this tail as well, even though there is, in fact, it has to counterbalance the original harmonic oscillator confining behavior. And we are now extending our approach to spin-isospin dependent correlation and to larger nuclei. And to do that, we are encoding, as Fiala was mentioning yesterday, we need to be able to encode the symmetry of the problem in the net. And this is what we are doing right now. And of course, in the future, we plan to access excited states and nuclear response functions. And with that, I thank you for the attention.
Thank you very much, Ole, for this very nice talk and on being on time. And we have again time for discussion and questions. So let's look in the chat box here. So Francesco Pereira is asking, can you expand on the relation with quantum computing you mentioned in the end?
Yeah, so I mean, quantum computing is really ideally suited to the real-time evolution. So it would be nice to map the very same problem on the very same nuclear problem in a machine learning framework. So basically the idea is that we parameterize the same initial state in terms of an artificial neural net, and then the imaginary time evolution is encoded in the imaginary time evolution of the weight and biases of the net. And we see whether minimizing this distance as a function of time can reproduce the imaginary time evolution that you see on quantum computers for the same system. So for example, you can even think of, as you did in your work, freezing the coordinate and just considering the spin, the imaginary time evolution of the spin system for a given set of coordinates. And one in principle can do that with the net as well. And of course, at some point, this has to, you know, I mean, I think it's intrinsically interesting to see and test the representation power of the net in this kind of problem as well, not only in ground state problems, for ground state problems.
All right, thank you. And then Thomas Poppenbrock is have a question here regarding computational scaling, and how does the number of parameters of the ANN and the minimization steps scale with mass numbers?
Yeah, so that's a good question. So what we did, I mean, what we did, we used the same net for all three nuclei. We tried smaller net and larger net, but the energy was basically the same. I mean, not much smaller net, but say like a fourth of the nodes, the energy wouldn't change. So here you can do this on a laptop, basically, for up to helium-4 with spin as a spin-independent correlations. Now, if you do the backflow, if you use these backflow ansatz, you have to compute this later determinant. So that costs you the number of particles to the cube. So that's the scaling. And when you compute the expectation value of the potential, for example, on this backflow correlation of the two-body potential, that's another A² factor. So basically, in addition to the computational cost of evaluating phi, you have an overhead of A to the 5th. But of course, you can use tricks, you know, not to update all the columns of the matrix. So, but roughly, it's an A to the 5th scaling with the number of nucleons, with a two-body potential, and A to the 6th with a three-body potential, which is still polynomial. It's not too bad.
Yeah. Okay, and then Alessandro Ruggiero is asking, how many parameters did the Jastrow wave function require? Is it much less than the 10 to the 4 for the ANN?
Yeah, that's true. But here, this is a purely central Jastrow. And as Ale know, we devised this together. It's like a spline. And if I try, so in total, it's like maybe 100 parameters. But if we extend, you know, if you double the number of parameters to 200, you don't gain anything, basically. And the reason is that this Jastrow ansatz is not the most general function that you can write, a particle function that you can write, because it's a product of 2 and 3. And even the 3 is not the most general one. So even if you increase the number of parameters, you do not necessarily get the same flexibility that you have with the neural net.
Okay. Let's see. I have a question regarding the comparison you had in the end there with the Green's function Monte Carlo and the ANN predictions for the energy and the density.
Yep.
So I don't fully understand. So the density, the agreement there looks almost perfect, right?
Yeah.
Well, we know that the density falls off with the separation energy of the nucleus, which does not agree with the Green's function Monte Carlo. So how do I reconcile that, looking at the differences in the energy and the densities being basically identical here, which is not what I would expect if you did
Yeah, sure, but the difference is not too big. I mean, the difference in terms of of the separation.
Yeah, the tail will fall off exponentially given by the separation energy, right? So
right. But the difference is between the Green function Monte Carlo and the variational neural network is small. I mean, it's like so you don't see that basically. But what I was most interested in here was to make sure that the harmonic oscillator confining functions that we use at the beginning of the optimization procedure is completely compensated by the net, and this is apparent in a sense. So yeah, you're right. There is probably the exponential is not exactly. I mean, the separation energy is not perfect, but it's not too far away from the exact one, because sigma 1, 2 here is small, of course. I mean, the spin-dependent term in the potential is small. This pi and less EFT potential are almost SU4 symmetric, so yeah.
Thank you. And then let's see, Morten Hjort Jensen has a question. Have you tried neural network Jastrow as input to the GFMC DMC machinery? And if, how does it compare with standard VMC inputs?
Yeah, so in this case, since this is basically, we are just modifying the Jastrow, we're not changing the nodes of the wave function if you want. So I expect the final answer to be the same. Maybe the error bar is going to be smaller. But our goal is to define this spin-as-spin dependent trial wave function. And even if they are not perfect, even if we don't get the same energy as the GFMC, we very, very much want to use them as input for GFMC calculations, because they must have a much larger overlap with the exact ground state than a linearized spin-dependent correlation that we typically use.
Let's see, Francesco Pereira was asking another one. Can you imagine using a similar approach for the backflow?
Right, so this is somehow a generalized backflow ansatz. So basically, in typical backflow, what you do, you replace so in typical calculations, you have single nucleon functions here. So phi1 of x1, then you have phi1 of x2, and then, in the backflow, you have x1 and x2. And here instead, you correlate all particles. So that's the difference. And it's not just the backflow. So it's not related to the speed of the particle propagating, but it's this generalized correlation correlates the position of and the spin of particle 1 with the spin and the position of all the other particles. So it's a little bit more general than a backflow, but the spirit is exactly the same as the one of the backflow.
You also added a comment there. This changes the nodes ... So I don't know, Francesco, if that answered your question.
This changes the nodes, yes. This changes the nodes of the wave function, yes, it does.
Okay. Any more questions? We still have a couple of minutes before we move on. Please raise your hand or add a comment. Arno has a question. Arno Rios. What is the mean field reference state that you use, and how far is it from the final solution?
Yeah, so in this, that's a good question. So in this in this first application of the neural net, the Jastrow correlator, the mean field is basically doesn't even have coordinate space dependence. It's basically a Slater determinant of spin and isospin. So for the deuteron, for example, it's just the proton. It's a Slater determinant of proton up, neutron up. So it's really literally proton up, neutron up minus neutron up, proton up. That's the reference state. So if you want, it doesn't know anything about the radial dependence of the wave function. Everything is learned by the net by minimizing the expectation value of the Hamiltonian. And here instead, if you want, it's the opposite. So here, if you want, the Slater determinants knows everything about the wave function, but it has to learn it, and the hope is that it does. And I have to say that it works in condensed matter applications for quantum chemistry, but sometimes this backflow is supplemented by a JASTRO just to improve the training convergence, but this has to be tested.
Okay, thank you. So we are 11:30 here Eastern time, so I think we should move on to the next. And thank you so much, Kjell, for this very interesting talk and discussion. And moving on to the next speaker, James Keble from University of Surrey.
Hey.
And, he will be talking about towards a machine learning description of nuclei. And yeah, we have about 10 minutes or so with a 5 minutes discussion. So please go ahead.
Sure. Good afternoon, everyone. Firstly, thank you for the invitation. And today I'll be talking about my talk on towards the machine learning description of nuclei. James Keble from the University of Surrey, and I'm a PhD student. Okay, so my talk's going to be broken down into kind of two sections. So firstly, I'm going to talk about solving the deuteron, which was mentioned in the previous talk. And the reason why we started with the deuteron is that it's quite a good benchmark to use, because you can exactly diagonalize the Hamiltonian and get an exact result by which you can compare any numerical results which you can get from a machine learning approach. The interaction that we use to describe the deuteron is an N-MATLAB n-free low potential, so it has the S state and the D state included. And we take this problem and we separate the center of mass from the relative motion so that we reduce this to an effective one-body problem. And we also solve this within a momentum space as opposed to real space, as a kind of a way to get around to the expensive Laplacian calculation. And the framework of was PyTorch as opposed to TensorFlow. So to talk about how we represent the wave function of the deuteron is by a simple feed-forward neural network, which takes the single input node, which is the relative momentum of the deuteron, and passes it through a hidden layer of arbitrary width, which is 5 hidden nodes in this diagram, and it outputs the S wave function and the D wave function. And the activation function of choice for this network was the soft plus function, which you can see on, which is kind of a continuous form of the ReLU function, if you're aware of that one. And we also use the sigmoid function as well to kind of compare between a bounded function and an unbounded function. So what we do is we initialize the weights in the range you see in the top left here for both layers, and then we provide a arbitrary target wave function for the S and for the D state, so that the initial shapes that are produced by the network are kind of physically sound, because just with this default initialization, the wave function is very flat and it's hard to minimize directly to the ground state. So once we've given the network this target wave function, we maximize an overlap with the network and this target wave function. And then once we've achieved this, we can then go into minimizing for the energy. So once we've kind of pre-trained the network, we can just calculate the expectation value for the energy and then just directly minimize from that. So the integration scheme that we use for this is a Gaussian quadrature mesh of 64 points. And the optimization scheme that we use to optimize our weights is RMSProp. And all RMSProp is a modified form of steepest gradient descent, where you have this kind of velocity term on the top here, which is just an exponential moving average of the square of the gradient. And this is just used to modulate your learning rate, so that if you're in kind of a flat region of kind of your minimization landscape, you're going to take larger steps to quickly go through it. Or if you're in a rapidly changing part, you're going to take smaller steps so you don't overshoot as much. And as you can see on the right here, you can just minimize the energy using the scheme, and you just converge towards the exact solution. Okay, so taking it a little bit further now and talking about the bias variance trade-off of the network, we can take our network, do the pre-training and then the energy training, to find the ground state solution for a given number of hidden nodes. And what we did here is we did this 50 times, and we took the mean and standard deviation, where the solid line here is the mean with plus or minus 1 standard deviation for the error bar for both the sigmoid and the soft class, and compared it to the exact solution. So as you can see here, with only about 6 hidden nodes, which is 24 variational parameters, you're already within 3 or 4 keV of the direct solution. And as you increase the size of this network, it kind of plateaus towards the exact answer with not much change in variance, which is a little bit counterintuitive, because as you expand this network even further up to 100 nodes, which would be 400 parameters, you would expect the variance to start to increase. That's given by the bias variance trade-off. And interesting enough, you don't see this initially in the energy, independent of the activation function used. But if you take this kind of approach of an ensemble of networks, and instead of looking at the energy, you look at the wave functions, you start to see where this variance is kicking in. So what we have here on the left is the S-state wave function for the neural network for both activation functions and the exact one from diagonalization, and the same on the right we have for the D-state. So what you can see here for a wide range of them, you have very good agreement between your network and the exact solution. The only areas where you have kind of a problem is for low value momentum. And this is somewhat to be expected, because if you look at the expectation value below here, you have this kind of Q squared, Q prime squared factor, which means that for low values of momentum, they're going to contribute very little towards your expectation value. So when you take the gradient of the energy, any errors at this low value of momentum is kind of going to be disregarded, and the network is going to favor making sure it fits higher values of momentum. And then as we increase the network size again, so taking kind of the 2 extremes in terms of the size, you can see where the variance starts to kick in. So this is the same plot as before, except that we've gone up to 100 hidden nodes in our hidden layer, which corresponds to 400 variational parameters. And you can see that for both the S and for the D state, regardless of the activation function chosen, that you get an increase in variance, albeit with kind of a constant energy. So just partially concluding the juice-ROM, we've shown that you can use networks like this to solve nuclear problems and get generally quite good agreement with the energy. We also shown for this particular case that the bias variance trade-off is pushed towards the zero cost, low momentum regions. And that is the kind of a nice starting point. But then taking it ahead, the challenges that need to be overcome would be to include anti-symmetrization and also including the spin degrees of freedom of the system. So just to briefly kind of mention that, work in this area has kind of been taken by kind of chemistry, and I'll briefly talk about solving the one-dimensional harmonic oscillator problem. So this network here is inspired by FermiNet, and this type of network is anti-symmetric by design. So you take your linear layers, which I'd mentioned in the previous network, and you replace it with what is called an equivariant layer. So all this layer is it takes in some vector input, which in our case is just the one-dimensional position for each particle, and then it outputs kind of a higher order representation in terms of size, which you can see in a bit more detail at the bottom. So you have a kind of one-dimensional position here, it goes through and it gives some H sized vector, which represents it. And the reason why you want equivariant layers is because eventually once you pass it through enough layers in your network, you're going to pass it through a slated determinant, which is going to enshrine the anti-symmetry you need. And you need to make sure that the input to that determinant is equivariant, so that a change in inputs corresponds to a change in rows in your determinant. So once you have that, you can just take the determinant and you can get a neural network, which by design is anti-symmetric. And just to briefly talk about solving this for the 1D harmonic oscillator. This is just a solution for the 1D and 2D case, comparing the network in blue and the ground state in red. And you see there's generally quite good overlap. This is solved within real space as opposed to momentum space. And just taking it a little bit further in terms of more particles, it's hard to represent it for greater than 2. you can see that you get quite good agreement here with up to 5 particles surface as far as the taking it at the moment. So to conclude, you can solve the Deuteron with an artificial neural network and get quite good results, around 0.1% in the error for the energy with constant variance. The bias variance trade-off is pushed towards the origin for this type of network, and you can actually construct anti-symmetric networks for larger bodied systems. And many thanks to my collaborators and STFC as well. Thank you.
Thank you very much. So we still have a couple of minutes for discussion and questions.
Yeah.
So let's see. Morten Hjort Jensen is asked, no, sorry. Giuseppe Calero is asking here, what features are you using in the equivalent layers? Few particle distances or other things?
No. So for this at the moment, kind of skip through this quite quickly. All I'm taking is an individual position and then with an invariant property of this input vector, which in this case is the mean. So you take your input vector here, calculate the mean, and then attach this onto each input node. And then what you can do is you can have just a standard linear layer, which takes, say, 2 inputs here, outputs H outputs, and then share this across all of the inputs so that one, you can increase the representation of, say, your one dimensional position, but also it's equivariant by design. So kind of the equivariance is maintained by just the swapping of the inputs.
Let's see, now we have another question from Jane Kim. Can you elaborate on the pre-training of the network?
Yeah. Okay, so just a slide here to talk about the pre-training. So once you've constructed your network for a given number of nodes, the wave function itself is very kind of shallow. You see here in the dashed line for both the S and the D state, it's very flat. So what we do is we give it this kind of arbitrary training function, which is defined here at the bottom right for the S and for the D state. And then we just maximize the overlap, which is defined here. So you start with a very flat wave function initially. And then once you've trained it, you get something that resembles this target wave function. Again, you still get this issue with low values of momentum where it will have kind of high variance there. But that's just to make sure that the network produces physically sound shape, because it's easier to minimize the energy of this wave function on the right than it is to minimize this wave function on the left.
Right, so he said thank you. And any other questions? So in the figure where you show the Deuteron and converging comparison with the exact result, did it seem like you flatten off slightly above the exact result?
Yeah, so there's kind of a bias, assuming kind of like this bit here,
right,
where it doesn't really seem to reach. So one issue that we found is that there is this kind of bias regardless of how large you make the network. One idea with that is that the learning rate we use is quite large. So if you had a kind of a learning rate scheduler, so the learning rate would reduce over time, that would help it reduce it as well. But one of the key issues with the energy, if I can get to the slides, is that there's a slight kind of difference. Sorry, let me just get to this. Right, so this plot here will help kind of explain this discrepancy in the energy. So what I have here is the kind of the difference in the integrand for the exact wave function and the network's wave function for the potential energy. So the top left here, you have the S state interacting with the S state, and then SD here, DS bottom left, and then bottom right is the D state. And one thing that if you kind of take an element-wise difference and plot it as a heat map, you can see where some parts of the wave function are kind of adding an error, or they're kind of over predicting what the energy should be, and then some other areas of the momentum are underneath. So you can kind of see an element-wise error for each kind of contribution towards the potential energy, if that kind of makes a bit of sense. Mm-hmm. So with, for example, if you were to reduce the learning rate and make it, let it kind of evolve for longer, or even adding in more layers can help. But the main point of this was to have the simplest network possible to solve this problem.
Right. And then let's see, Alessandro Lovato raised a hand. So if you want to mute yourself and ask the question.
Yeah, so thanks for the talk. My question is, so do you think like that you don't converge the exact energy because of like training efficiency, or is it because like you're, if I'm not wrong, you're working on a momentum space grid, right? So like you are effectively discretizing the integral over the momentum. So have you tested how much your results depend upon this discretization? Like, are they totally unaffected, or maybe there is room for that? Because the difference is pretty tiny, so it could be that, right?
Yeah, quite possible. We haven't actually played around too much with the spacing of the grid. The main two issues that I kind of came across were learning rate and this issue with increasing, if you add an extra layer on, which kind of defeats the point of having a minimal working example, you can get slightly better improvements, and also having kind of the plateauing learning rate. So initially you take quite large steps, and then it kind of fine tunes itself in kind of this kind of hundreds of thousands limit for the iteration. But the grid could definitely play a part of that as well.
Okay. Thanks.
Okay. I think we are time to move on. So thank you, James, for a very nice talk, and
thanks
to everyone for the questions, discussions, and moving on to the last speaker today, Krishnan Raghavan from Argonne National Lab. Will talk about PIS-NN, a machine learning approach to invert nuclear responses.
Hi, just give me a second. I'm sorry. Can I interrupt you? Hi. Just trying to make sure if everybody is seeing the screen and can hear me clearly.
Looks great.
Okay, thank you. Thank you for the opportunity for me to give a talk. My name is Krishnan. I'm a postdoc at Mathematics and Computer Science Division in Argonne National Lab. My talk is going to be about trying to invert nuclear response functions of and I'm going to present a method based on machine learning neural networks. Now, so the outline of my talk is basically I'm going to start with the problem statement. A good part of this, good background about this problem statement was given by Alessandro earlier. So I'm just going to briefly overview it and talk about the challenges in that problem. Present our methodology, which is a PIS-NN, and with some description about the data set and the results. So to briefly introduce, what we are trying to do is to understand how atomic nuclei and neutrinos scatter when incidented with some energy. The way it is generally described is by a response function, which completely encapsulates all the energy and the dynamics of the target, which is measured by electron scattering experiments. However, as Alessandro mentioned earlier, we do not measure this response function directly, but we measure an integral transformation of the response function. In this case, we are considering an integral transformation weighted by an exponential of omega tau, which is essentially your Laplace transform. So you get your Laplace transform, you want to go back to the original response function. So obviously you have to build, you have to come up with some way of inverting a Euclidean function to a response function in a compact form, which can basically be written as a matrix inverse multiplied by the Euclidean. That's how you extract the response function. Now, this inverse is essentially ill-posed, and because of the fact that multiple response functions can have the same Euclidean response within errors. And then moreover, because high noise in the Euclidean response can lead to unstable inversion. So the problem is ill-posed. And while solving the problem, we have three major physical attributes that we want to maintain in our approach. One is the idea that our integration of the response function has to coincide with the original Euclidean responses. The response function has to be positive definite, and the response functions that the model we developed has to capture the structure of the response function, which is basically one quasi-elastic peak and multiple peaks at the low omega region. That kind of structure has to be captured. So to take into account all of these structures into a model, we write our response function as this equation here, which is basically 1 by n being the normalization, exponential, and function output function here. Now, to this whole equation can be basically represented by this network that is shown as follows. This network essentially has three components. First, to capture the structure of the response function, which is one quasi-elastic peak and some multiple peaks in the low omega region. We have a mixture of Gaussians that we use. Which we use to form a basis over the response function. Then we use a neural network on top of it to perform your final inversion. To make sure that the Laplace transform of the output response function, which is what you get at the output of the neural network, coincides with the original one. We also extract the estimated Euclidean response from the output of the neural network using the Laplace transform. And essentially, we will try to build a learning problem, which does constrains the estimated Euclidean to the original Euclidean and constrain the response functions in the middle to the original response function. Now, let's take a look at each of them in a step by step. So first, starting with mixture of Gaussians. So the basic idea here is to take for each Euclidean on a basis of on some tau value, you define a series of Gaussians which basically span the space of eta. For example, if your eta, I'm making this up for a particular tau value, maybe 0.05, and eta is, let's say, for example, spanning between the range of -5 and 25, you will put multiple of these Gaussian functions, which will basically transform the input eta into such a way that it is spanned, it basically lies on the curvature of these Gaussian functions. Now, when you use this curvature and do things with it, you can assure that the basic structure of the response function, which is some kind of a Gaussian type structure, is captured by this approach. So when you collect all of these Gaussians, each Gaussian is basically given as a sum across. For each eta, you have multiple Gaussians. For each Gaussian, you have a mean parameter and a variance parameter, which is where is the location of this Gaussian curve and how much is the width of the Gaussian curve, both of which is going to be a parameter that we are going to learn as part of our network. Now, using this parameter, you get this vector, which is your series of G's. Now, this series of G, that is the output of this layer, is given to a neural network where it's basically multiplied by W's. And that's how you get the output after all the W's is. And that output is basically your estimated response function, which you get. Now, to ensure that this output essentially follows a positive definite structure, that's the second condition that we want to, physical condition that we want to apply on our network. We will apply an exponential function over that, which will ensure positive definiteness. Then we will normalize with n0, which is essentially dividing with the value of the first Euclidean estimated Euclidean value at tau 0, so that the response function output, which is this output, essentially coincides with the Euclidean. The integral coincides with the Euclidean, which is essentially given as a Laplace transform of the estimated response function. Now, given this estimated Euclidean and estimated response function, therefore the overall network basically goes from e tau to e hat tau, and in the middle you get the output of r hat, which is your response function. Now, given this response function as well as your estimated Euclidean, you want to construct a learning problem in which you minimize a loss function, which as a function of the actual Euclidean, the actual response function, and the estimated response function, and minimizes those to parameters theta, where we estimate that theta is given as a collection of the mean vector of all the Gaussians, the variance vector of all the Gaussians, and the weights of the neural network. So to estimate, to apply this last function, we essentially have two components to it. One is we want to constrain, I apologize, there is a typo here. This should be an E instead of R there. One part is to constrain that the Euclidean, estimated Euclidean looks like the original Euclidean, such that the integral constraint can be applied. You choose chi-square as the cost function there. Then to ensure that R hat looks very, very close to the original response function, then you use the entropy as the cost function there. Both of them are weighted by some values, which are chosen arbitrarily as part of the optimization problem. Now, to test this network, which is essentially a combination of Gaussians and the standard neural network, a cost function given with entropy and chi-square, we generate a synthetic data set. We consider two cases. One first case being the top right plot, which essentially has a single quasi-elastic peak with no low omega region. And the second structure is one quasi-elastic peak as well as a peak at the low omega region. We compare our approach to a well-known standard approach in inversion, which is maximum entropy. And we use three metrics for this comparison. One is the R-square value, then is the entropy value, and third one is the chi-square between E and E hat. So R-square and entropy are calculated between the estimated response function and the actual response function. And chi-square is only calculated between the actual Euclidean and the estimated Euclidean. So let's look at the overall numbers. First of all, we observe that maximum entropy, all the overall numbers for chi-square values on the Euclidean lie very, very close to 1, which is as expected because maximum entropy is trained to fit such that the Euclidean looks like 1. On the other hand, for the phys-NN, the chi-square values over the 1 peak, 2 peak, and the case in which combined are varied here. Now, in this case, we are showing results from 3 realizations of our network. One is in which the whole network is trained only on 1 peak data. The second realization is when the whole network is trained only on 2 peak data. The third realization when a network is trained with a combination of 1 peak and 2 peak data. So obviously, 2 peak, the combined result is somewhere in the middle of 1 peak and 2 peaks, which is as expected. On the other hand, when you see the maximum entropic performance on the entropy values, you see that there is a significant improvement in terms of phys-NN's performance compared to maximum entropy performance. Now, quickly, to see the spread of this performance over a set of 1,000 data points, which a test set which we do not use as part of our training, we observe that if we see the spread, we observe for all the 1,000, chi-square is very, very close for maximum entropy, whereas more spread out for phys-NN. On the other hand, entropy values are much smaller for phys-NN compared to entropy, compared to maxent. On the right side, what you see basically is what we were telling before is that there is more correlation between the chi-square values and the entropy values of phys-NN as relative to max entropy, which is expected because max entropy is designed that way. Now, let's look at the 1 peak reconstruction. In 1 peak reconstruction, this plot was shown by Alessandro as well. Basically, original is given by blue, the phys-NN is given by orange, and max entropy is given by green. You see max entropy is able to capture structure, phys-NN does a little bit better, but not significantly, and max entropy does very well. In the 2 peak set is where you see a lot of difference in reconstruction from max entropy. Before going there, I would just like to show that the result that we saw in terms of spreads on the 1 peak data set is almost equivalent on the 2 peak data set as well. The main thing to note here is this structure here. You see that although the maximum entropy is able to capture the quasi-elastic peak very well, it completely fails to capture anything in the low omega region. On the other hand, phys-NN is able to capture the low omega region very well. And this is even in the worst response reconstruction for our method, we are still able to capture the low omega region very well. So to analyze it further, we kind of did an analysis in which we calculate the entropy value with respect to omega and plotted it as a function of entropy as a function of omega for both Maxent and entropy. So the larger the value here, the better alignment there is in that region. So as you see in the low omega region, the larger the value here, the poorer the alignment is in that region. So as you see in the low omega region, there is poorer alignment for maximum entropy compared to physenon, which is consistent with both one peak, which is the result on the left, as well as on the two peak, which is the result on the right. Furthermore,
sorry to interrupt. If you can wrap up in a couple,
yes,
2 minutes, that would be great. Thank you.
Yeah, it's my last slide. Sorry about that. Thank you. So another price that we want with our neural network to have is to have noise resilience with respect to noise. So here on the right plot, we see that when we increase the noise from 10 to the power -3 to 10 to the power -4 to 10 to the power -3 in our data set, we see that max entropy completely has a much more drastic change in its performance compared to physenon, which is also seen on the left plot, where the difference in change in max entropy is significantly larger compared to the noise level. When the entropy function is plotted as a function of noise level, the difference is larger for max entropy compared to physenon. So in conclusion, by taking into account the structure of the physics into the problem, we were able to show that our method can significantly outperform maximum entropy. We have better alignment in the low omega region with respect to maximum entropy. And as a future work, we would like to provide ways in which we can propagate errors in the Euclidean responses to the output response function in terms of predictions. Thank you for the opportunity. I apologize that I went over time. Thank you for the opportunity again.
Thank you very much, Krishnan, for this very interesting talk. I think we can still have a couple of minutes for questions. And Ale, did you raise your hand?
No, so raise the hand. Yeah.
Did you want to ask a question? No. Okay. So maybe I can ask a question here. So you if I understand correctly, you train the network now on the one peak and two peak sets, right? Artificial sets that you train the network on, and then you make some predictions. But in real applications where you might have more peaks or where you don't know what the peak structure is, how would you expect these networks to perform?
So
function.
So the way we train this network is the two realization which are shown for the purpose of illustration, where in which you train it only on one peak and only on two peak. And the third one is when you trained it on a combination of one peak and two peak. The price element of the problem, the end price of the problem is the neural network that was trained on both combined peaks. So as long as in this training data, you have data corresponding to all the different realization that you can see in the real problem, you should be able to use this network trained on a set of all of those data to invert a real world Euclidean response. Does that answer your question?
Yep.
So the model trained on the combined data set is the end price, and that's what we have to use, which is trained both on one peak and two peak.
Right. But you could envision you have more than just two peaks in the response.
Right. So that's what I'm saying. So you will have to have some representative sample from data more than two peaks in that set on which you train. You will not be able to expect a network trained on one peak and two peak alone to be able to predict maybe, let's say, 4 peaks. I'm making this up, but you will have to have a representative sample in there. However, that being said, the performance will not be equal. You know, something that is only trained on one peak will obviously be better performing than something that is trained on two peak, while on something that is trained on all of them together. So the performance will split, for lack of a better explanation term.
So what is the perspective now on using these on real world applications?
I'm sorry.
What is the perspective for applying this approach now to actually calculate real world response functions?
So you basically, let's say I get an exhaustive list of different peaks data and I train and give you a model. You just take it and apply, give it input as any Euclidean response, and then get your output predicted response function. That's all there is to it. The perspective is that to elaborate it better, the better your initial sample input is, and the more it covers the actual response functions, how it looks like, the better this network will be.
Mm-hmm.
So it will be data oriented in that sense.
Okay, thank you. Anyone else wants to add something? Questions, discussion points? I don't see anybody adding questions to the chat box. So, okay, I think then, thank you very much, Krishna, for this very interesting talk. And thank you to all the speakers this morning here on the eastern side in the US, at least, or evening in the US, Europe. It was very interesting talks and discussions. And yeah, thank you very much. And I think that completes today's session. And we start again tomorrow at the same time.